Good evening, everyone. A very warm welcome to all of you. I'm Neelam Parshuram from IC Ventus team. Thank you for joining us once again this Tuesday. For those who are attending this for the first time, welcome to our weekly webinar industry series, where every Tuesday we connect professionals, experts, and learners from the elevators and escalators industry to one common platform. While we wait for a few more participants to join in, I'll take a few minutes to explain what does IC do and how does we work with industry. So ICE platform is designed to share practical knowledge, industry insights, real world experience that can help you grow professionally and stay updated with the latest developments in the industry. We are glad to see participants joining in from different location, and we truly appreciate you taking time out of your busy schedule to learn, to gain insights, and to upgrade yourself with us today. So it's an initiative by IC Ventus. IC Ventus also organizes exhibitions, trade shows, and industry events. We create a platform that supports learning, collaboration, and business growth. IC Ventus have become a trusted bridge connecting regional markets with global opportunities. Our upcoming events. First is IC India 2026 will be held on 3rd, 4th and 5th December in Delhi, proudly making capital city the host of this year's edition. With the strong industry support, IC has grown to become the world's fourth largest exhibition for elevators and escalators, reflecting the trust and collaboration of the entire industry. This year's expo is planned across a massive area of 40,000 square meter, featuring 350 plus exhibitors, making it one of the largest gathering for the vertical transportation industry. So get ready and plan your visit accordingly. We will recommend at least to plan for 2 days visit to experience the scale of this expo. Next show is it's called IC, the Monsoon Edition in Chennai, featuring the Quiz, Symposium, and Dynamic Industry Expo, scheduled for August 5th, 6th, and 7th in Chennai Trade Center in 2027. The Monsoon Edition reflects the Chennai's regional weather calendar held before the monsoon season. It creates a perfect time for the industry professionals to network, plan upcoming projects, and discuss solutions before the operations slow down, typically caused by heavy rains. Next is IC Africa 2027 will be held from 24th, 25th, and 26th November in KICC, Nairobi. As you may know, Kenya is emerging as one of the fastest growing market in Africa for infrastructure and urban development, creating a significant opportunities for escalators and elevator industry. In this context, I see Africa 2027 will bring together global manufacturers, suppliers, and industry leaders to showcase safe, innovative, and sustainable vertical mobility solutions and drive growth across Africa's vertical transportation sector. Next is IC papers. So the vertical transportation industry has always been built on knowledge shaped by experience, innovation, and real world challenge. Yet much of this knowledge often remains scattered, undocumented, or limited to individuals and organizations. That's why IC Papers is created a platform designed to bring industry closer together. It's a space where you can share knowledge, showcase your professional journey, and even highlight your interest beyond work. It also helps you to connect with the professionals across the industry and learn more about the people you work with. In addition, IC papers will feature company profiles, researched articles, industry insights, and updates on events happening in the vertical transportation sector, all in one place. This platform is built by the industry and for the industry to encourage learning, collaboration, and growth. If you are part of the vertical transportation ecosystem, this platform is for you. So please do visit our website icpapers.com, and please do follow on social media as well. Moving on to our today's session, we are pleased to have with us Mr. Krish Theobald from B MAC Controls Pvt Limited, a leading expert in electrical installation standards and a member of BIS ETD 20. He will be speaking on elevator electrical installations. Are you up to code? Where he will explain the latest requirement under IS 17900 and the National Electrical Code SP 30 2023, and what they mean for your elevator installation. This session will be especially valuable for the professionals looking to stay compliant with the latest electrical standards. We will have a Q&A round at the end. So please, if you have any questions, please put it down in the comment box. With that, I will like to invite Mr. Krish to take over this session. Over to you.
Hi, Nilan. Thanks very much. Can you hear me?
Yes, clearly.
I'll just start to share my screen. Okay. Is the screen visible?
Yes, your screen is visible.
Okay. So, good afternoon, everybody. My name is Krish Theobald, and today I will be talking about residual current devices. Yes, I am here today representing a specific manufacturer who is, but I'm going to keep this as brand neutral as possible because my background is in standardization and I want to keep this as brand neutral as possible. So a little bit about me. I am a standardization specialist. I have membership in ETD 20, ETD 50, and CED 47 P13 working group features for another national building code. So I'm with the groups in BIS that work on the National Electrical Code and the National Building Code, Electrical Part Building Code, of course. I also represent India in the IEC, so the International Electrotechnical Commission, and in DC64. So I'm in several maintenance teams working. So I also lead a project team, which for some reason is not listed here. I am the owner and director of two companies, Doepke Schaltgeräte Private Limited and TNG Electrotech Private Limited. And I'm also technical advisor to B MAC Controls Pvt Limited, who is the India stockist for Doepke, which is what I'm here today. Products, but like I said, I'm going to use it as brand. So, who sets the requirements in India, right? So we have the Bureau of Indian Standards, and then we have the Central Electricity Authority, measures relating to safety and electric supply. And the point of this is that I just want to explain the regulatory framework and how it works. So in India, we have the Electricity Act 2003. This is enacted by the Parliament. And this act says that there shall be a body called the Central Electricity Authority. And this body shall make regulations for a variety of purposes, majorly the safety of persons, property, and livestock. And then we have installation standards, which are required to be followed as per the regulations. And then we have product standards, which are mentioned in installation standards. So product standards say you shall select a product conforming to this standard. So the Electricity Act is enacted by Parliament. The CEA regulations, measures relating to safety and electric supply 2023, has now been amended in 2026 as well. Very recent. So that doesn't really affect the elevator industry so far. The amendments. Yeah. Then we have the installation standard as well. So in India, we have the National Electrical Code of India, SP 30/2023. And we have IS 7, is the code of practice for wiring installation. And then there are product standards like IS 12640 Part 1, 624, 609 Part 2, etc. What does it say in the Electricity Act? It says in Part 14, Section 146, that whoever fails to comply with the provisions of this Act or rules or regulations made thereunder shall be punishable with imprisonment. And it also says that in Part Section 149, that if this offense is committed by a company, then anybody who's in charge of that company is liable to proceed against and punish. This could be director, manager, secretary, any other officer who's guilty. So we have a pretty solid regulatory framework at the minute. So yeah. Now, what are the key documents that I want to talk about today? So obviously, two of these documents are the National Electrical Code and IS 732, which we already mentioned. But there's also the document that is very relevant for your industry, which is IS 17900 Part 1, which is the lifts for the transport of persons and good Part 1, which is safety rules. This document is obviously everybody knows about this document, and there is a link between these documents as well. And I'll show you that link in the next slide. So what is the relationship with these standards and IS 17900? Because in the presentation, I'm going to be talking largely about IS 732 and NEC. But the important thing is that these are actually integral within 17900. So if you look at clause 5.10.1.2.1 in IS 17900, which is protection against electric shock generally, it says that the protective measures shall comply with the provisions defined by IS 732. So with regards to protection against electric shock, you have to comply with IS 732. In IS 732, it says, whenever necessary, provisions of this code shall be read in conjunction with other codes, such as those on earthing, lightning protection, and the national electric. So IS 732, so 17900 says you have to follow IS 732, IS 732 says that it shall be read in along with or in conjunction with National Electrical Code. And the National Electrical Code, specifically in Part 1, Section 10, says that we're talking now about electric shock specifically. So it deals with protection against electric shock as applied to electrical installations, and it is based on 4.2 of IS 732. So it brings back here, which is a basic safety standard that applies to protection of persons and livestock. So 17900, 732, and NEC are all interlinked. SP30, by the way, is just the BIS is designation for the country. So what is a residual current device? What does it do? And what are we here to talk about? So there are four broad categories of devices that fall under residual current devices: RCCBs, RCBOs, CBRs, and MRCBs. I'm going to focus mainly on the RCCB and RCBO for this webinar because I want to keep it relatively compact in the interest of time. So an RCCB is a residual current circuit breaker without integral overcurrent protection. This is a device that basically provides protection against electric shock, fire. What are the use cases, etc.? We will talk about later again. I'm not going to get into fire much because this is specifically for electric shock, because that falls under the purview of 170. Product standards are IS 12640 Part 1, so IEC 61008, and IEC 62443. The RCBO is a residual current circuit breaker with integral overcurrent protection. This is a device that provides protection against electric shock, fire, and overcurrent as well. Think about it simply, an RCBO is like an RCCB plus an MCB combined in one. Its product standard is IS 12640 Part 2, which is an adaptation of IEC 61009 Part 1 and IEC 624. So this is like an MCB plus RCCB, and this is just the RCCB. Obviously, now you have much more compact version. This is a very old picture just taken for illustrations. Before we get into the actual requirements in the standard, I want to just give you a little bit of information about the types of electric systems that we have that are designated by IS 732 and NEC. See, each electric system is designated a 2 to 4 alphabet code that explains what kind of system it is. First alphabet designates the relationship of live parts to Earth. Second alphabet designates the relationship of exposed conductive parts to the body of equipment to Earth. And the third and fourth letter, which are supplemental, not always required. They designate the arrangement of Earth, live, and protective. Don't get too bogged down by this. I'm just going to briefly explain what this is and what the implication is for you as someone in the vertical transportation. So the first thing is that we have a TN system, particularly TNS system, and this is a little bit of information on this. So in a TNS system, the live parts, so which is the transformers windings, the star point is connected to the general mass of Earth, so it's directly connected to exposed conductive part, which is the body of the equipment. This is also directly connected to the Earth point of the power system. So there is a metallic fault, there is a metallic return conductor going from the body of the equipment all the way to the protective conductor back to the transformer star. There is a direct connection of the Earth point to the power system. So T means that the source is directly connected, N means that the load or the equipment is also directly connected back to the Earth point, not to the general mass of Earth, the Earth point. And this letter S designates that the Earth live conductor, in which case is the neutral conductor, and the protective Earth conductor, these are kept separate throughout the instrument. There are two separate. This is a 5-wire system that we have here. Now, what you will realize is if you have a fault here between the body and the phase, let's say L1, amount of current will flow through is very high. It is similar to a short circuit. Yeah, because you have a very negligible amount of it. There is one more type of system, which is a TT system. So there are many TN systems. There are TNS, TNCS, TNC. But what I want to focus on is just the TN part, which is that if you have a fault, an earth fault, there is a lot of current that flows through, enough current to cause interruption to it. Maybe an MCB or a fuse, etc. Then we come to the TT system. This is a system where the live parts are directly connected to the earth. So the first alphabet is a T. But unlike there being a protective conductor back to the source, which is what we have here, you have a connection of the exposed conductive part directly to the general mass. And this is when you have a small problem. The problem mainly is that if you have an earth fault between the line conductor and the protective conductor, or the line conductor and the body vehicle, the amount of fault current is limited by the resistances of these electrodes and the actual soil between. So in the event of a fault of negligible impedance between the line conductor and the protective conductor of the body of the equipment, unlike in the TNS system or any other TN system for that matter of fact, you will have a very small amount of current. So in this case, you may have thousands of amperes. In this case, you may have 1 or 2 amperes. If we look at what is the situation in India, so before I do that, so you see this is a 4-wire system. So you are getting only 4 conductors from the DISCOM, L1, L2, L3, and N. You look at the system in India, we generally have a TT system because we are only getting a 4-wire supply, L1, L2, L3, and again, L1, L2, L3, and L1, L2, L3, L1, L2, L3, L. So there's an absence of a distributed protective conductor. So we have essentially have a de facto TT system. This slightly we pivot now to what the RCD is and how it works. So an RCD is a residual current device, as we know, and as I explained. There are 2 types that we want to talk about in this webinar, which is the RCCB and the RCDO. But in general, we'll use the term RCD because they apply to all those devices. There are 3 reasons why you use an RCD in any electrical installation. Today, I want to focus specifically on fault protection. The standard requires that in clause 4, IS 732, that you must have disconnection in certain times provided in these clauses. This is generally 1 second, 5 seconds, 0.2 seconds, or 0.4 seconds. For an elevator, generally this time would be approximately either 1 second or 5 seconds, depending on system or thing. But for certain smaller elevators, it could even be 0.4 or 0.2 seconds. But in general, let's assume 1 second for TT system, which is what is in this clause. Requirements for the earth electrode and protective conductor resistance are such that the resistance of the earth electrode multiplied by the rating of the RCD in milliampere shall be less than or equal to 50 volts. So the sum of the resistance of the earth electrode and protective conductor for that particular equipment, your lift in this case, multiplied by the resistance of by the rating of the RCD, the rated residual operating current shall be less than 50 volts. This is the classic equation. Fault protection in a TN system, as I explained, you have a lot of current that will flow through. So enough current to cause adequate fault current to cause operation of an OCPD during an earthquake. But in a TT system, let's say this has a resistance of 100 ohms, for example. So 230 volts divided by 100 ohms, we're talking only 2.3 amps of current. There is inadequate fault current to cause operation of an OCPD during an earthquake. They are limited by the resistance of the earth electrode in the installation. So essentially what happens is that you don't have enough fault current. The other way of looking at it is that instead of just considering the resistance of the earth electrode, you can also consider the overall loop impedance because that gives you a fuller picture. The resistance, so the sum of this entire impedance times the rating of the RCD has to be 50 volts or less, right? So again, disconnection times are, as I mentioned previously, given in IS 732, but generally for an elevator, 1 second is the applicable time. So yeah. Now, when it comes to achieving this disconnection, it's very important that the correct classification of RCD is chosen. There are 4 types of RCDs available in the market. This is not about the RCCB, RCB, or CBR, MRCD. This is to do with the classification according to the presence of DC components and frequencies other than their rated frequency. So if we talk about the type AC RCD, this is an RCD that can only detect alternating current residual current at main frequency as per their product standard. The type A is an RCD that can detect AC residual currents and pulsating DC residual currents as per the main frequency. And correct tripping is only guaranteed at 50 Hz of residual current. Type F is a device that can handle AC and DC with some different frequency components, but the main component has to always be 50 Hz. And type B can handle DC and other frequencies. The first thing that I want to bring to your attention is that the type AC RCD is predominantly what is used generally in India. I know in the elevator industry, in the vertical transportation industry, there is also adaptation. Type A has also been adopted, and some limited players have also adopted type B. But the important thing is that if you look at countries like Germany, Sweden, Denmark, Australia, New Zealand, these people have banned the type AC. And outside the elevator industry, 99.9% of all RCDs are type AC. So this has been banned. If you look at NEC, we're not allowed to use these in these applications anymore. But unfortunately, predominantly, this is what is being used. What are the applications for this type B RCD? Because again, we're talking specifically about what is relevant to your industry. So the National Electrical Code SP30 says RCDs of type B shall be used in case where the application may create small DC residual current or contain frequencies higher than 50 Hz. Further information is provided in IEC 6036453. It says that this kind of RCD can work for residual direct current, which may result from rectifying circuits. For example, 2 pulse bridge connections line to line for 2, 3, and 4 pole devices, or 3 pulse start connection or 6 pulse. Anyways, I don't want to get into the technicality. This is just for those who are interested. But what are the actual applications that are mentioned in the National Electrical Code? We care about what's there because that's what's referenced in 1.7 and B. It has type B RCDs are required for inverter, battery backup, UPS systems, variable frequency drives, including lifts and escalators, which is mentioned in clause 5.4, section 10, part 1 of the National Electrical Code. Also EVSC, so EV and solar PV. But again, if I look at what's written in the clause 5.4, it says RCDs of type B shall be used in case where the application may create smooth DC residual current or contain frequencies higher than 50 Hz. For example, 3-phase class 1 device containing a motor controlled by 3-phase variables. This is basically what we have in most of the. You have a variable frequency drive and it is a class 1 device, so it has a connection for the protective conductor. And also other examples are three-phase air conditioner pumps, etc. What happens, you see, is that when you have a fault current when you have a fault within these devices, the type of fault current is not a sinusoidal alternating current. It is a chopped up waveform that is generated. How is that waveform generated? I will explain. So let's just talk about a situation where we have an RCD protecting a three-phase rectification circuit, and then after this you may have a VFD, and we look at those specific cases. You may have the IGBT. But basically, in this situation, you have if you have a fault here between any line in this DC bus, the overall fault current is the sum of what happens when the first phase peaks plus the second phase peaks plus the third phase peaks. So IF is equal to IL1 plus L2 plus L3. And what happens when DC residual current occurs? So if we talk about this specific example again, in the first cycle, you get a peak, then for 2 cycles, nothing, then another half cycle run. Once again, third. And what is the combination? IF, it looks like this. So it looks like you're getting these peaks superimposed upon a certain level of smooth DC. Now, if we talk specifically about the case of an elevator, if the fault happens before the VFD, then you're just going to get 50 hertz. A type A is sufficient in these cases, right? However, if you have a fault that occurs in the DC bus, then a type B is required. Why? Again, like I said, during the first phase's half cycle, you get a peak, then nothing. Second phase, the peak is offset by 120 degrees. Third phase, it is offset by 240. Resultant is peak, 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 peak over a certain smooth piece. And only the type B RCD can interrupt a situation like that. If you get a fault current that is happening after the VFD, between the VFD and the motor, for example, then you get whatever frequency is the VFD is outputting, which is usually not 50 hertz, right? That's how you control the speed of it. So this is what you get. And once again, type B. Important thing I want to explain here is that if you have a fault between the frequency converter's output and the motor's frequency is say 10 hertz. But very importantly, the chopper, which is these IGBTs here, this may be operating at a frequency of 8 kilohertz to generate this 10 kilohertz frequency. As a result, the actual fault current will look like there are different frequencies that are superimposed on the residual current. So we may have 16 kilohertz, 24 kilohertz, 22 kilohertz. There are harmonics of that particular component. And even a type A would fail to detect this. It's essentially what happens is that type A's core becomes saturated and it's no longer able to disconnect. So that's relatively important. If we talk about this particular manufacturer, Doepke, which is what I'm to talk about, again, generally I've kept this plan neutral, but just for an example, something that you need to verify is can your device actually operate for this entire band of frequencies up to say 8 kilohertz as an example. See, the key thing is what is the relationship between frequency and electric shock? There's a standard called IEC 60479. It's prepared by a group in ICD 64 called Working Group 4. I was involved. And this shows that as the frequency increases, the threshold for the amount of current that can cause ventricular fibrillation or your heartbeat to stop in the event of electric shock also increases. And you need to make sure that the characteristic of the RCD that you are choosing is also such that it follows this pattern. So in this particular case, this RCD is disconnecting before this threshold of ventricular fibrillation. And crucially, this RCD has to be able to operate for all bands of frequency that the elevator may generate due to the operation of the chopper. So this particular manufacturer, we go up to 150 kilohertz, so 150,000 hertz. Yeah, this rotation of people and equipment. Now, just a comparison, not all manufacturers are able to produce something similar. So, for example, this product can stay in the correct zone, which is the green line, but some other manufacturers, even the Type Bs, the other manufacturers, they go all over the place. And this has to do with one of the most important problems that are reported on the field, especially I know from a lot of our clients in the elevator industry, which is unwanted tripping. Because if, see, on the x-axis I have frequency, on the y-axis I have current. If the elevator is, say, outputting a 8 kilohertz frequency, or in this particular case, say a 10 kilohertz frequency, this is a 300 milliampere device, for example. This particular red line has this product tripping at a value of, basically, I believe this is 60 milliamps. So 300 uh, milliampere device is tripping at 60 milliamperes here. So that is when you have a nuisance tripping situation where you have a lot of fault current that is flowing, or rather you think it is flowing, but it is not. It's just the frequency is high. So in the absence of an actual fault, because remember this equipment has some filters inside, what is that, how does that look, I'll get to it. But basically, even 60 milliamp can end up tripping a 300 milliampere device if the wrong type of RCD is stored. So we have two extremes. The first extreme is if you use a type A or a type AC, which is what is used everywhere, the device can get stunned. The second is that because the frequency response of the device is such, it can start nuisance tripping much earlier. So that is why the selection of the right type of RCD is important. And many times on field, I know that people remove the RCD, then they replace it with an MCB or they just bypass it, right? And that defeats the purpose. You're not achieving protection as per what is required in the standard. How do we deal with unwanted tripping? So basically, there are a couple of things. One thing is the frequency, but the other thing is making sure the RCD is not overloaded, essentially. So if I talk about this, the important thing is that the sum of residual currents downstream of an RCD should not exceed this value of 0.3 times the value of the rating of the RCD. So for a 300 milliampere device, we know this because it's sold a lot in the elevator industry. 300 milliamperes into 0.3 is 90 milliamperes. So you cannot have more than 90 milliamperes of leakage current connected to one 300 milliampere. How do you figure this out? I'll get it. And obviously, if you're having many final circuits, use an RCBO for these circuits. That solves that problem because then you have dedicated RCDs for circuits. Now, you may ask me, what is the source of this leakage? The first thing is that leakage current doesn't occur in the event of a fault. In fact, leakage current is defined as current flowing in the absence of a fault. But to an RCD that is sitting over here, for example, okay, to an RCD that is sitting here, it may look like we have a fault. And why is this, right? So you have a filtering capacitor in the circuit here, here, and here, and this is required for EFCs. To this filtering capacitor, you have current flowing like this, also like this, and like this. And for the RCD, it looks like some amount of current that is flowing through here is bypassing the RCD. So it appears like a fault. How much current is this? You see IEC 61140, which is the standard here. This standard, it talks about how much protective conductor current is permissible for equipment, including variable frequency. Because, yeah. And it mentions that the amount of current that is allowed to essentially leak depends on the rating of the equipment itself. So if you have a device between 0 to 2 amperes, you are allowed 1 milliampere. Between 2 amperes and 20 amperes, rated current of the device, you are allowed 0.5 milliampere per ampere. But if we talk about, for example, 15 amperes, you have to allow 15 into 0.5 milliampere per ampere. So 7.5 milliampere for this particular. And then if you exceed 20 amperes, you're allowed 10 milliamperes max. But important thing which is for you guys is that the protective conductor current using equipment for permanent connection, which is what an elevator is, which is having a protective conductor current greater than 10 milliampere, you're allowed to have it not exceeding 5% of the rated current. So for example, if your elevator is using 50 amperes, 50 amperes into 0.05, which is 5%, technically you are allowed even a 2.5 ampere of leakage current for a 50 ampere device. And it can get tricky. Obviously, in practice, this is quite rare, but I've seen 300 milliampere, 500 milliampere on a certain elevator, especially those with regenerative drives. How do you prevent unwanted tripping? So the first thing is you have to select the device correctly so that the frequency bands are taken care of, like we explained. And then you need to sectionalize. So if you have a 100 milliampere RCD, 100 times 0.3 is 30 milliampere. So sum of all connected equipment downstream, the leakage current should not exceed 30 milliampere. 15 plus 15 is 30, this is fine. This is a 30 milliampere RCD. 30 times 0.3 is 9 milliampere. So 333, here it is 9. This is 300 milliampere. 300 milliampere times 0.3 is 90 milliampere. So 45, 45, 90. Now, importantly, this is also 300 milliampere. So 300 times 0.3 is 90. But sum of this is actually 30 plus 9. So again, less than 90 milliampere. So you're fine. But in India, unfortunately, we see something very different. Oftentimes, this is again not very true for the elevator industry, but we have 130 milliampere RCD installed for the entire installation, and then this will trip. Or one 500 milliampere RCD, but on the circuits that require 30 milliampere, like for example sockets or lighting, then you have a shock risk. So these are the problems that can occur. Anyways, like I said, I'm going to keep it short and sweet. So again, this is the company in India that sells this Type B RCD. So thank you for your attention. But like I said, I'm here to attend and have a discussion with you all to, see what doubts you have, and I'll keep it brand neutral.
Thank, thank you, Krish, for
Thanks.
the information and insightful presentation.
Sure. If you want to stop sharing my screen, you will have to do that. Yeah.
Acha, I'll do that. Attendees, we will now move on to our Q&A round. So, anyone want to ask any questions, please put it down in the comment box.
Anything you want to ask in relation to the devices, applications, etc., I'm more than happy to answer. Like I said, I'll keep it brand neutral.
One question is, you showed us that VFD creates DC components in the residual current. Why is a type AC or even type A unable to disconnect in the presence of DC?
Okay, so thanks for whoever asked that question. I think it might have come in anonymously. Yeah.
Yes.
So, okay, so what essentially happens is that in an RCD, in a type A or an AC RCD, you have a simple toroid. And when current passes through this toroid, say you have 1 ampere here, 1 ampere here, it appears perfectly balanced. There is no net magnetic field induced in this toroid. So nothing happens. When you cross a certain value, you there is a when there is an imbalance, say for example 1 ampere flowing here
Are
and
you
point,
sharing a screen? Sorry.
sorry,
Sorry.
yeah. Is it not visible?
Yes, it is not visible.
Sorry, I will. Okay, let me
Yes,
just
yes, we can.
erase all the marking and then I will see. Okay. So you basically in every RCD you have a toroid like this red circle over here that is sitting, and it is monitoring how much current is going through the line conductors, how much current is coming back to the conductor or the yeah, or any of the other lines. Now, say we talk about a single phase load through L1, we have say 1 ampere, and through neutral we have also 1 ampere. Now we know that when current flows, alternating current, which is a changing magnetic field, flows through a coil, a current is induced in that coil. But now here the current in and the current out is the same, so there is no current. But say for example, instead of 1 amp, 1.0 amp flowing through here and 1.0 amp coming out through here, you get 0.9 amperes flowing out. Then there is a net current, alternating current flowing through this of 0.1 amperes. And that will induce a current inside this toroid. The type AC and the type A RCD works by using that current to cause the contact to disconnect. That is how a type AC RCD works, and that is how it works. When you have DC current, which is what happens in this particular case, this component here, this component here, this is the DC component. When you have, from basic elementary physics in school, we know that when a DC current, which is there's no changing magnetic field, flows through a coil, it will become magnetized, but there will be no net current that is induced. And because of that, the device is not disconnecting because there is no net current in the toroid. Because of that, you need sophisticated equipment to filter out that DC component and then use it to signal. Or if it is purely DC, then to detect that DC and send a trip signal. So because a type AC and a type A RCD rely on a conventional toroid and a fundamental alternating, the presence of an alternating current at the rated frequency being 50 Hertz, that is why they can trip. They are a very simple device. They just have a toroid that sits around the conductors, and when there is a current, it disconnects. That's it. So to answer the question that was asked, a type AC or a type A RCD will essentially get magnetized. It will not be able to trip because there is no changing magnetic field created by the residual current. That is what happens.
Let's move to another question.
Yeah.
Next question is from Mr. Arun Agarwal. Thank
Yeah.
you for a nice presentation. As a standard, currently most of elevator company provide ELCB with 300 MA. Is it correct practice?
Yeah. Okay. Thank you, Mr. Agarwal. So the first thing is that the first thing I want to talk about is this ELCD versus RCD business. Uh, so in the market, we only have available RCDs, which are either RCCPs, RCBOs, CVRs, and MRCDs. Colloquially, to speak, people say that people call this device an ELCB. An ELCB is actually an earth leakage circuit breaker. It's no longer available in the market. It has a completely different operating principle. But in this particular in this case, most times when people are referring to ELCB, they refer to this RCCB device. When it comes to the rating, 300 milliampere may be correct, may not be correct. It depends on two things. Firstly, if we go to the slide that I have on this value, you need to measure the fault loop impedance in your TT system and see what is this fault loop impedance. Say you measure it is 100 ohms. Yeah. Then 50 volts divided by 100 ohms gives you this value of I delta. So 50 volts divided by 100 ohms gives you 0.5 amperes. So 50 volts divided by 100 ohms is equal to 0.5 amperes or 500 milliampere. In this particular case, anything less than 500 milliampere or 5.5 ampere is appropriate. So if this was the case, for example, this was the way to do it. Other way of looking at it is that we know that your I delta is 300 milliampere in this case. So 50 volt divided by 300 milliampere, which is 0.3 ampere. So 50 divided by 0.3. 50. So 50 volts divided by 0.3. This gives you a value of about 167 ohms. So if your fault loop impedance in the steady system is greater than 167, is lesser than 167 ohms, then 300 milliampere can be used. But the most important thing, sir, is to make sure that you have the right type of RCD. Because, as I mentioned here, if the RCD is a type A or a type B, which is not tuned to the correct frequency, or a type AC, two things may happen. Number one, it may get stunned, as the previous person had asked, and then it will not trip at all. Or number two, because the chopper frequency is very high, and that is the nature of the residual current, your 300 milliampere RCD may trip at, for example, 60 milliamperes, and then you have nuisance tripping. So to answer your question, sir, 300 milliampere Is it right or is it wrong? Is it a correct practice? That depends on the application. But more importantly, is it the right type? It has to be type B because that is what NEC requires. See, if you go back to the slide on what NEC requires, it is clearly mentioning here that three-phase class 1 devices containing a motor controlled by variable speed drive RCD of type B shall be used. So this is what it is. Yeah, I hope that answers that question.
Thank you. We will move on to our next question. It's from Mr. Pradeep Golder. MRL type lift feeding 63A type CMCB. It is a 12 passenger lift. Please advise RCCB rating.
Okay. So the first thing is that you need to find for the RCD there are multiple parameters that apply. So let's just go back to the picture of the RCD and I will show you what I mean. I don't know if you can see very clearly in this picture, but this RCD is rated to 40 amperes. That is the rated current, and the rated residual operating current is 30 milliamperes, so 0.03 amperes. First thing is if you are using a C curve 63 ampere MCB, this rating has to be at least 63 amperes. So you would in your case specify a 63 ampere rated RCC. Second thing is what is the rating of the residual current? Now you need to figure out what amount of residual current your drive is creating. The drive data sheet will specify this value. If it does not specify, you need to perform a measurement. So for example, I know that Doepke and B MAC, they do a measurement for people as well. But if you have the tool, you can do a measurement yourself. Then you have to find out what is, let's say you find out that you are getting 200 milliamp, let's say you're getting 70 milliamperes of leakage current from that particular drive, right? In that case, what do you do? So remember what I said here. Let's say you find out you're getting 70 milliamperes. The standard requires that the rating of an RCD shall be such that sum of all residual currents downstream shall be lesser than 0.3 times the rated residual operating current. So that means if we are getting, say, for example, 70 milliamperes, 70 shall be lesser than or equal to 0.3 times the RCD value. Let's call that R. So 70 divided by 0.3, which is 233. So R is supposed to be lesser than or equal to, or R is supposed to be in this case greater than or equal to 233. Yeah, so basically you need to make sure the RCD has a rated residual operating current of at most 233 milliamperes. Or sorry, in this case, more than 233 milliamperes, because here we are trying to prevent nuisance. So that is the case. Now 233 milliamperes is a non-standard size, so then you have to go to 300 milliampere. So if you use a 300 milliampere device, this is fine. What is the type of RCD to be used? Type AC, A, F, B. What is the type to use from this list? Well, you know very well that NEC says that you have to use type B in this particular case. I think I can see the question, Neelam.
Okay, yes, yes.
If we are using type C MCCB, then also weight connect RCD. The characteristic of the MCCB or the MCB or the overcurrent rated device is independent from the characteristics of the RCD. So that's irregardless of what is the type of MCCB, you have to also use a residual current device in the DT system, which is what we have on India. Yeah. Mr. Ravi, first of all, thank you for valuable presentation. In case of reagent type elevator drives application like Otis, are we need to increase the tripping sensitivity? Okay. Okay. So the first thing is that you need to figure out for this, it's again similar question to what the question before this was asked. What is the leakage current in this drive under normal situations? When I have that data, I can say, if you tell me 15 kilowatt, 5 to 15 kilowatt, I can tell you how much current that is. That is a very simple thing. But what sensitivity is required, this depends on how much leakage current this drive will create without a fault. And for that, sir, I have to use a data sheet. I need to check the data sheet. or you need to hire a company to do a measurement. For example, BMAC, who is the partner for Doepke, can do this measurement for you, and then they can recommend a part for you. So it's by just by knowing the rated kilowatt, I cannot recommend a particular thing because I'm not familiar with this reagent type, and I know from manufacturer A to manufacturer B, the leakage current is wildly different. Again, see, remember, the manufacturers allowed up to 5% of the rated current as leakage. So accordingly, you have to spend. And that's how you have to figure it out. I think there are no further questions, but if anybody wants some time to put some more questions, we can be there.
Attendees, if you have any further questions, please put it down. There is one more anonymous question.
Okay.
A practical issue on site is the nuisance tripping
Yeah.
of RCCBs. Does
Yeah.
using a Type B RCCB can help with this?
Yeah, I'd say particularly for for elevator applications, this is very important because if you use the wrong type of RCD or type B even that is not tuned to the correct frequencies, as I showed in this graph, a 300 milliampere RCD can trip with 60 milliamperes of leakage current. So absolutely to answer that question, using a type B, the correct type B that is tuned for the frequency that you require, in this case, for example, okay, can go up to 150 kilowatts. That's more than 150 hertz. That's 150 kilowatts. That's more than enough. It will prevent nuisance tripping in this case. So yeah, to answer your question, yes.
One more question. Most contractors we work with have never even heard of a Type B RCB, at alone
Yeah.
installed one. Where do we actually get this from in India, and what do we need to tell our team on site?
So where do you get one? I mean, again, B MAC is one of the stockists for this product in India. So I would say go to B MAC because I'm representing B MAC. But yeah, you can. There are people you have to go to specialist wholesalers essentially that have this type B. What to tell the guys on site is don't get confused between the type B RCD and the type B MCB. So MCBs are also available in categories. So for example, MCBs are available in B, C, D, and then some have K and Z also. And RCDs are available in AC, A, F, and B. This B and this B have nothing to do with each other. They are just letters that the ICE standard has used to designate it. I know the fact that they are both B's are quite confusing for people on site, but the first thing is that so you go to a specialist who understands this subject, and second thing is that tell your guys on site that a B type MCB is very different from a B type RCD. And this gets even more confusing when we talk about RCBOs. Because if you see in this particular RCBO in this particular example, the RCD part of this RCBO is type B, but the MCB type of the overcurrent rating is type C. Now it may be type B here and type AC here. That does not mean that the overall RCD is a type B. So you need to verify that the RCD's characteristic itself is type B. So to tell your guys on site, don't get confused between the RCD's characteristic and the overcurrent characteristic. They are two very, very different things. Yeah.
Can we move to next question?
Yeah.
Uh, Mr. Ravi is saying that if you feel free, kindly share your presentation, please. Thanks, Ravi.
I
You
mean, I'm
can,
happy to, if
you can,
Neelam, you can share it with you and you
you
can
can
circulate.
connect later, huh? Yes. Next question is from Mr. Arun Agarwal. How do we find leakage current in the elevator drive system?
That's an excellent question. And to show you the to answer that question, I am going to can you stop sharing my screen?
Yes.
I will show you a data sheet, and that will give you an idea. Okay, just a second. I need to open up a data sheet. Uh, let's just take a particular manufacturer. They are required to basically um, declare this value. I'll just give you an example. I don't know, again, I'm not very familiar with the actual drives, but if you tell us the actual drives, we can then tell you. But this is just an example. So let's see this thing. So yeah, rather than actually showing you something generic, I would say that uh, better would be for you to give me a drive and then I can tell you which one it is applicable. But to as an example, I can tell you that certain drives will declare that they have a maximum amount of leakage current, say 70 milliamps. So how to find it out? You will get that data from the manufacturer. If they don't give it, you need to write to them. As a manufacturer of a variable frequency drive, the IEC standard for variable frequency drive requires you to declare this value. So you are all with reputable companies will obviously purchase a drive from a reputable manufacturer who will design it to the right standard. They are required to tell you that. And again, if we talk about something that's on site, I know B MAC can come and perform measurement for you on site to tell you what your actual amount of residual current is, and then you can figure out what is the time of RCD to be used. Yeah. There's another question, which is how to select RCD for hydraulic lift. Just as you would for any other, I don't know what the difference between a hydraulic lift and a normal lift is. Again, I'm not an elevator person, but with the data sheets, we can get in touch. So again, my contact details I will display again on the screen. Uh, Feel free to get in touch with us, and then we can help you from a case to case basis. This is the partner that is there. We can discuss this. I think Neelam, I can give my contact details also that you can send out. Send out
Sure.
any specific technical questions, but for product related questions or how to specify the products, VMAC can help you out specifically for all this.
Can we move on
Anything
to
else?
next question?
Yeah.
Next question is anonymous. How to select RCD for a hydraulic lift?
Yeah, so I already answered that. We can-
Okay, okay. So, yes. Any other questions from the attendees? Krish, I think so. That's all from the attendees side.
Sounds good.
Yes. I would like to thank you once again, Krish, for sharing your expertise and addressing all the questions. Hope attendees are satisfied with the answers. And it was really an informative session.
Thank you very much.
Thank you
Thanks
for
to
your
you
time. Yes.
for the. Thank you.
And for the audience, thank you for joining us today. Your presence and participation means a lot to us. It keeps us motivated to like keep organizing such knowledge sharing webinars and initiatives for the industry. As a reminder, our session happens every Tuesday. Our next session will be on 21st April. I just say thank you once again for joining us and let's stay connected. Thank you all. Have a good evening.
Thank you.
Thank you, Krish.